Okay, example 6 is kind of a continuation of an example we saw back in chapter 2. We're creating boxes again. And in chapter 2 we kind of set up the problem. In chapter 3 we're going to try and actually find the optimal volume of this thing based on specific criteria for making the box. And this is a little bit more elaborate box also. Before we just had a piece of cardboard, we were folding it into just a nice open box. Now we got a box with a bottom and a top. This kind of flips over here. It's got a reinforced front there, kind of like a pizza box maybe. And if you imagine this is your bottom of your box and then this lid closes on top of it. What I want you to get a feel for in these problems is I want to get a feel for what the base is. So we're trying to create this box. It's going to be a rectangular solid. The base of this box is that, or this one over here. Take your pick, doesn't matter which one. All right. The challenge of this problem is to get the correct dimensions, because a rectangular solid's volume is length times width times height. So if we can establish those three dimensions, we can get all the information we need. So the set in stone value here is, this is 42 inches right here. From the first piece of the cardboard to the edge of the cardboard over here. All right, that's it, 42. We're cutting x, x, x out of that 42. So what's left for this piece and this piece together is 42 minus 3x for both of those pieces, right? Yeah. And these pieces are equal in size, so if I divide that by 2, it's going to be how big that piece is. So this little piece here and this little piece here is simply going to be 42 minus 3x all over 2, which reduces to 21 minus 3x over 2, maybe 1.5x even. Most people like decimals better than fractions. So we can go ahead and, since we got a friendly decimal, we can go ahead and do that. We got an ugly decimal, leave it as a fraction. I'd rather have the exact number instead of the approximate number. But 1.5 is nice and pretty and easy to work with. So that's the length of the base. The width of the base is this length here. And notice this is 18, and we're taking x and x off it, so 18 minus 2x is the width of this. So I got a length of the base is 21 minus 1.5x. The width of the base is 18 minus 2x. And the height, oops, ahead of myself here, the height is simply going to be x. Okay. And again, sometimes people see x, x, maybe it's 2x, but everywhere there's a dotted line is where it's going to be folded. So it's going to be folded up and then back over, so it just has a reinforced side. There's what's going on there. So there's my dimensions. Volume is always length times width times height for a rectangular solid. So volume is going to be, I'm going to actually put height in front. I like my single letter x in front. Times length times width. So 21 minus 1.5x and 18 minus 2x. I'm going to have to FOIL this. Going back to what you guys saw in Algebra 2 today. The other class has seen before where you just multiply and you add kind of thing. This has coefficients in front of the x that doesn't allow for that shortcut, so be careful. 21 times 18 is 378, I think. Yeah, and 21 times negative 2x is negative 42x. Negative 1.5x times 18 is going to be negative 27x. And 1.5x and 2x, both negative, becomes positive 3x squared. And then all this I have to do is combine like terms right here and distribute that x through. I like descending order, so I would probably end up with 3x cubed, multiplying x times that. These together make negative 69x, multiplied by x makes negative 69x squared, and then plus 378x. So notice it asks us, I probably should have noticed that before I started working the whole problem. What do you think x looks like? It looks like a letter in the alphabet. I always read the directions. It has asked me to do this kind of stuff. So anyway, a closed box be constructed from this, the box be made by cutting that, blah, blah, blah. What value of x to the nearest thousandth inch will produce a box with maximum volume? We're trying to find maximum volume, so it makes sense to find a volume formula. Okay, so what I've done so far, good ideas. So now that I've established that the volume formula is this, the other thing I want to establish, and we talked about this back in chapter 2, was domain. All right, I need my dimensions to be positive. Okay, x is greater than 0 creates that situation at least. All right? There's also a high end of x also. If we go too big on x, we're going to be negative again because 18 minus 18 is 0. So if x equals 9 here, then this is going to be bad. So x has to be less than 9 for that one. And here, 21 minus 1.5x greater than 0 gets me negative 1.5. X is greater than 21, which means x is greater or less than. That'd be negative 21. Like 14. So 14 plus 14 plus 14 is 42, right? So we take 42 away from 42, we get no box, okay? So x has to be less than 14 and less than 9 and greater than 0. It can't be less than 14 if, sorry, I should say it can't be less than 9 if it's like 13, right? So this isn't any help to us. Usually you get two less thans and a greater than. The two less thans, the one that's smaller less than is the one that's more important. So x has to be between 0 and 9. So x is equal to some number between 0 and 9. That's important because, again, our graph lives sometimes in the negative region. We don't want any of those numbers. We want to know where it's positive. We want the volume to be positive. There's going to be a part of this graph with x cubed, but what we just saw is, you know, if you get a graph that does something like this, you know, maybe even gets back to positive again somewhere over here because you have two negative dimensions. All right, you could do something like that. We're looking for this part of the graph here. So that's what we're looking for. So make sure that you do this much thought. So you're looking only at the part of the graph that matters to us. All right, we're trying to maximize volume here. We're going to use our calculator to do it for us because we haven't learned calculus yet. Because typically use calculus to maximize things. If it were a parabola, x squared, we have a technique for maximizing that, right? We find the vertex. Okay, cubic functions don't have a vertex. They have high points and low points, but we don't know what they are, and there's no set in stone formula. This is how you do it, all right? At least not with this class. So 3x cubed minus 69x squared plus 378x is our function, our volume formula. I'm going to set my window on x from 0 to 9 because, again, we've established that's where x lives. As far as the y minimax, y represents volume. 0 volume is going to be the smallest volume possible, all right? I have no idea what the maximum volume is. What I usually do is I kind of estimate that's 20 times 40 is 800. I'm going to guess it's probably less than that. Might be a lot less than that, but I mean, if you just kind of estimate these to the nearest 10 and multiply that area of that piece of cardboard to begin with, the volume's usually less than that number. If it goes off the screen, you know it's not, you can make it bigger. So it's kind of a play with the thing. I'm going to go with a 100 scale on that. It doesn't matter what the scale is. Hit graph. And, oh good, it worked. All right. As long as you see the top of the graph, you're in good shape. If the top of the graph is way down here, you went way too big. If it goes off the top of the screen, you can go big enough. But that looks pretty good. All right. And we can see the maximums occurring in here somewhere, but I can't tell exactly what it is. Now, a couple ways to get there. If I hit trace, what trace does is it puts a blinking cursor on the graph. And notice it's at 4.5. It's right in the middle. If I go left, it's 4.4318, blah, 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 and so on. I'm watching the y's as it keeps going up. Bigger, 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 bigger. 606.53 is the biggest?
5.4. Well, it's 536.4.
There it is. All right, so 606.53644, and then it starts going back down again. So 495324. So right here is the biggest one that ends up on our trace. But it's going by a specific increment, okay? And that's how your calculator actually graphs. However big, what it does is there's so many pixels between that 0 and 9. They divide 9 divided by that number. That's how much they go up by for each, and they just pick a point for each one, connect the dots. That's how the calculator graphs things. Okay, so all it's doing is picking those exact spots. Now, if I want to get the exact biggest volume and the best value of x, okay, I'm going to go to my calc. So I go up here above trace. So I hit second calc. And notice number 4 is maximum. That's what we're looking for, right? So that's probably a good one to pick. I'm going to just touch 4. It immediately takes you back to the graph. If you use cursor down to 4, you enter either way, but you should come to the graph. It's going to look for 3 things from you: a left bound, a right bound, and a guess. Okay, I've already established the answer is around 3.54, right? Left bound is something below that, right bound is something above that, and guess is something between those numbers you pick. 0 and 9 are the limit. I can't pick -5 and 74 because they're off the screen. As long as I stay between 0 and 9, something less than 3.54, I'm going to go 2. I can actually type the number 2, or I can just cursor over some, hit enter. All right. For right bound, I'm going to pick something bigger than 3.54. I'm going to pick 8, because it doesn't really matter. Okay, I'm just based on giving the calculator a window here. I want to find the answer between these two values. We can see the top happens between those, right? Right. You don't have to get super duper close. In the past, some students, I need to get really, really close to this, and then they pick for me. So just make sure you're on the screen and that the top happens between your boundaries. And as far as the guess is concerned, I could guess 7.9999, my calculator. There's only one maximum value between those numbers. Pick something between 2 and 8, because that's what I picked. I'm going to pick 3.5 because that's close to what it was. If you pick something close to what it was, the calculator finds it faster. 3.5706. So 3.5 is said to the nearest thousandth of an inch, and thousandth would be 3 decimal places. So 3.571 inches. Okay. It asked what value of x will produce the box with maximum volume. If it says what is the maximum volume of the box, Vmax, then we would go here. It would be the 606.5597, so 606.560, 606.560 inches cubed. If it asked what dimensions of the box would be the maximum volume dimensions, once you found out what x max was, then you'd have to go here and here to establish the length and width of the base along with the height. So again, depending on what they ask, the calculator is giving you some information. It's your job to interpret that information properly. So x equals the value of x that produces the maximum. Because again, we can see here this graph represents volume. It's 0, goes to a high point, goes back to 0. Right? The value of x that made the maximum is right here. The volume itself is right there. So again, x represents how big x is. Y represents volume of the box we're creating. So again, depending on what they ask you for, make sure you know those things. And again, if they ask for the dimensions that produce the maximum volume, or what would the dimensions of the box with maximum volume be, once you know what x is, use your length and width expressions to establish the values of lengths and widths for that. Use the proper units, and again, round properly. On the last test, I had a few things where I specifically said round to a certain number of decimal places. I did deduct points if you didn't, so make sure that you're looking for that type of stuff. This one here, though, nearest thousand, 3 decimal places, 3.571 inches produces the maximum volume box.